Welcome. So we will start a new module. So we learned about aquifer. We learned about groundwater flow and groundwater flow equation, well hydraulics, and also we looked at that like when you start pumping or injecting or whatever. In this module, we'll bring all these together. Like whatever we learned, we learned a little bit about like groundwater surface water interaction. In this module, we will like kind of connect the dots, like bring all these together. So here, these are some good textbook if you want to learn more about this. So we will in this module, you will learn how to set up and calibrate a groundwater flow model. For this, we use a code called MudFlow. So MudFlow, is a code, a computer code that solve your groundwater flow equation with all these different parameters like pumping, injection, boundary condition, recharge. As you will see, like all these, MudFlow has all these packages. Yeah. Here, if you want to learn more about like how to develop like a conceptual size model, including the subsurface characterization. Here, if you want to learn more about like boundary conditions, how to set up like and conceptualize like your boundary condition. This book is not free. It's about like if you want to learn more about model calibration and uncertainty analysis, which we will be also doing in this module. And this book, like in your textbook, chapter 13, that's more or less similar to this slides here, but with more detail. So if you want um, like a more elaborated version, then you can check it here. Okay, so let's start our first lesson in this module, which is the introduction to groundwater. So by the end of this lesson, you should be able to describe the modeling process, the groundwater flow modeling process, or the modeling process in general. Like what like the modeling process in general, like so you'll be able to describe this and then you will be able, so that's one objective you'll be able to describe. So the modeling process is like how you create a conceptual model, you set up your model, you calibrate your model, you apply your model, you document your model, you implement the solutions that you proposed, and then you do post auditing. That's the modeling process. Identify the main component of the conceptual model and the data requirement, like how to set up a conceptual model and what are the data requirement for that. Okay, so let's get started. So this is your Facebook activity. Okay, so the modeling process, I would rather add one more here. Learn groundwater hydrology. So the first thing is that you need to understand what you're doing. That's what I was just telling you in a minute ago. Like we learned about aquifer property, we learned about the flow equation, we learned about flow to wells. So you need to, if I understand something, I can model it. Yeah, and I cannot model something without understanding it. Yeah. So you need to learn, you need to have this, like you need to build your model on a solid ground, and solid ground is what we have been trying to do in these previous videos, yeah, lessons. Then, now you took a course like this, you have this knowledge, uh, and then the and then you are assigned something like this. Then you start like your data collection and like site characterization. Then you do like your model development, like conceptual model development, model setup, model calibration and validation, model application, and then you do post auditing and you update your solution. Yeah, so you implement a solution. Like let's say you are doing a remediation system. So you design this remediation system using this model, and then you will implement this design, and then you will see if it's working, if it's not working. If it's not working, you'll see why it's not working, and then you update your model, you update your solution, and so on and so forth. And modeling is very important in groundwater hydrology because we deal with this natural systems that are wide. Like I cannot get an aquifer and study it in the lab, unlike other things where you can get samples or whatever and study it in the lab. This like aquifers, these are things that extend spatially, like by kilometers, tens or hundreds or even thousands of kilometers, as like we've seen the Nubian sandstone aquifer, thousands of kilometers. So I cannot. So the way to study this and to manage these aquifer is that you create a model, like you bring this model to your computer. You create like a version of this model like in your computer. You calibrate it. Calibrating the model, you means that you make sure that whatever your model is producing is what you are observing in the field. If whatever your model is producing is consistent with what you are observing in the field, this means that this model is a good representation of reality. Just a good representation, not the representation, like a good representation of reality and of my phenomena that I'm interested in, and then I can use this model for my purposes, management purposes or scientific purposes or whatever. Yeah. So what are like what is a model? Yeah. So a model, like in groundwater hydrology, we differentiate like between like a conceptual model and a computational model. So a conceptual model, this is like a quantitative representation of the real world, like the real world groundwater problem or aquifer. But importantly, it is a representation that can be described mathematically, because on other field, by conceptual models, they mean other things. They mean that I just have like some understanding of something. So there is this phenomena, these are the drivers of these phenomena, and this is a conceptual model. In groundwater, it's not like this. In groundwater, a conceptual model is something, whatever I have for this conceptual model is something that I can be able to describe mathematically. And I will show you this in a minute. So it is something very specific, yeah. Uh, so in the conceptual model is based on like what is based on, like it's based on the available data, such as like the understand like the geological data, hydrologic data, any geophysical information, any expert knowledge. You collect all these information and you put it together in a conceptual model, and this conceptual model will include information about your geology, your hydrogeology, your groundwater recharge and discharge, and other factors that affect your flow and water and quality. Yeah. So you put all this in a way that can be described mathematically. On the other hand, in numerical model, this is the mathematical representation of your conceptual model. So now I have a conceptual model. When I uh, represented mathematically and then I solve it numerically, then this is a conceptual model. So basically, it divides your groundwater system into interconnected cell and solve the equations that describe, for example, flow or contaminant transport or whatever. Let me show you. So here, that would be like, so like, see, let's say that's a conceptual model. Yeah. Like you have some understanding about the geology. And a numerical model is that when I convert this conceptual model to a mathematical representation, and then I get like a numerical solution. So if I'm solving for head, for example, like this, I will find the head here. 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 That is if I'm solving for head. If I'm solving for concentration, it will be the same. I'll find concentration at different point. Yeah. So numerical model that requires like like you have like this input data from your conceptual model. So this input data from your conceptual model would be what? Like would be the boundary condition, would be the hydraulic conductivity, recharge rate, pumping rate. It will take this information from your conceptual model and simulate the behavior of your system. So why do we need conceptual model? Because conceptual models, they provide an understanding of the system and help us to identify data gaps and uncertainty, as I will show you in a minute. Versus we need like a computational model This is the one that makes prediction. If like you want to evaluate the effects of different management strategy as you will be doing in your modeling case study. So this will provide like a quantitative understanding of like the behavior of your system, and it allow you to test different like scenario, different management or future predictive future scenarios or whatever. Yeah. So here a conceptual model, see that's very important, a non-unique representation of your understanding of the system and can be described mathematically. This is the two keywords. Like it's a non-unique, it has to be, you can describe it mathematically. Why non-unique? I will show you this because different people could interpret data differently and you could end up with different conceptual model. A computational model, this is like a quantitative representation of the conceptual model, like mud flow and mud pass, as you will do like in your project. Yeah. Okay, so so what data do we need for for our conceptual model? Of course, you need site characterization data. Like so, site characterization data, you need to understand your aquifer. You need to understand like your boundary. You need to understand like land use and land covers, the geology. If you have some geophysical information, that will help you to understand some of this like geology and some of these like hydrogeological parameter. You need to understand the management, like who, like what are the different water use, who is pumping, how much they are pumping, what is management constraint. So all these, like you need to understand like pumping and water use data, like and management constraint, like what are the policies that govern like how water is used. Yeah. And then you need to understand, like if you're doing like some impact of climate change, you need to understand climate and the future climate and some future climate scenario. So this will be like that will fall under site characterization. So you need all this information to characterize your site. You need also to characterize your initial conditions. So for example, I'm simulating salinity from 1990 to 2025. So I need my initial condition. I need to know what was the salinity in 1990. I need to know boundary conditions. So like what is happening across my boundary? Like what is the flow rate across my boundary, or what is the head across my boundary, or what is the concentration across my boundary, or what is the concentration gradient across my boundary? Things like that, yeah? So you need also boundary conditions. You need site characterization, you need initial condition, you need boundary condition, and more importantly, you need data for calibration and validation. So remember, I told you, let's say I have a model here, yeah? And what this model simulate is it simulates a head. Yeah, that's what the model is doing. It like you solve for head, like you have your groundwater equation like delta H over delta T. So you're solving for H. So your model will give you H here, H here, H here. How do you know that this model is the true model? How do you know that this model is not like is like a good representation for your site? Well, the way to do this is that you get like data, like you go, like let's say I have, this is what my head is like head, like here. Let's say the model simulated head here. The head simulated is like 100. The head simulated by my model here, like at this cell, at this location, head simulated is like 105.1 meter. Yeah. Then then I go in the field and I measure the head there at this time. Yeah. So you have like this field data. So this is the head observed. So let's say the head that I observed was 103, for example, 0.5. See, there is a big difference between what my model is simulating. This is like about almost like more than 1 or 1.5 meter difference between what my model is simulating and what I'm observing. This means that this is not accurate. I need to improve my model, and that's the process of model calibration. You keep improving your model until what your model is simulating is consistent to what your are observing in the field. So let's say I'll update my model, I'll improve it. Improve it by what? Improve it by changing the site characterization, improve it by changing my boundary condition, my initial condition, that's how I improve my model. And then I run the model again, and then let's say now the new simulation will be like 103.4 meter. Now, see, this is a small difference. That's about like 10 centimeter difference. So that's a good difference. So this means that now my model can simulate what I am observing in the field at this location and at this time. Yeah. And that is like calibration data. But sometimes your model is not only producing head. So your model is producing head, is also producing discharge. Like if this is like a coastal model at a coastal aquifer, then you have discharge to the ocean. So that's called submarine groundwater discharge. So again, you measure, like you see how much at this location, how much submarine groundwater discharge my model is predicting. You measure it in the field. There is ways to quantify this also, and then you compare them. You could also be doing like not only a flow model, but also a transport model like salinity. So you could also check for salinity or nutrient concentration or whichever type of solute or contaminant you're interested in. Another thing could be like flow passes. That could be also something like certain flow passes from the field, and you can do this through isotope analysis or whatever, like age dating or things like that. And then you can compare this with what your model is producing. So that's another calibration data that you can get. Yeah. So that's basically the data that you need to develop a conceptual model. So let's look at a conceptual model. So here, this is part of a conceptual model. Remember, I showed you this at the beginning of the semester, this pharmaceutical site. So here, I have, so now I have like, this is my model domain. So I identified like my model domain here. Yeah, so I identified my model domain here. This is my pharmaceutical facility. I have the head here, so I have like a observation well. From this observation well, I measure the head and then I generate this head contour. So here is like 45, 40, 35. So now you are expert in this. You know like the flow direction from high energy to low energy. So water will flow like in this direction. So you can almost like trace it here. So water will flow here, water. So now you are expert in this, yeah? So now I was able to provide. So this is not what my model is producing. This is what I'm observing in the field. So these are the head values that I'm observing in the field. And this is what I want my model to reproduce. So if my model was able to reproduce these heads that I'm observing here, so if my model was able to reproduce these heads that I'm observing here, this means that this is a good model and this model represents my field condition and I can use it for management purpose. What else do I need for my conceptual model? I need to characterize the subsurface as a hydraulic conductivity field, and you did this before. So this is an example of one conceptualization. So we collected some data, and from this data we get this conceptualization. Now this model here, it has two layers. Like it has like a surface layer and a down layer, and this layer has like generally like lower hydraulic conductivities and like these surface layers. So this model has like two layers, yeah. So that is basically what also part of my conceptual model is that I conceptualize the hydraulic conductivity field based on the available data. What else? What else do I need? So remember, I need to know recharge, how much water is coming in. So this is a bird view, yeah? So this is a bird view of your aquifer. This is a side view of your aquifer. I need to know like how much like recharge, like how much this aquifer is getting recharge. So that's like another piece of information. So here, this is like a very interesting problem because see, this is my general flow condition, but inside the site, like at certain part of the site, I think it's like this part of the site. Like I'm just like, so this is my site. I'm just like zooming out to like one part here. You see, like if I plotted the head here, just like zoomed out, like just plotted the head here, yeah, it will have these like local anomalies, like local changing gradients. So you see very high head here and very low head here, which means that I have a source here. So means like there is a source of water, and probably this source of water would be a broken pipe. So there is a broken pipe in the subsurface, and this broken pipe is constantly like recharging my my subsurface. So I have like this general flow pattern here, yeah, in my model domain, but like only in this part I have this local flow pattern here because of this like of these uh, of these like recharge source. So that would be one hypothesis that has a broken pipe here. So that's how we conceptualize it, the different recharge. So you see here, like the recharge here is very high value, like 8,000 millimeter per year, versus the recharge in most of my model is 5 to 10 or even zero uh, uh, in some uh, or in some parts, yeah. Uh, like I'll be getting like zero recharge in some part. Okay, so this is just one conceptualization of recharge, yeah. Uh, This is just one conceptualization of recharge. But remember, in this model, I'm not only interested in doing like a flow model, I'm also interested in a transport model. So I have different types of contaminant and then I find their concentration. So this one, like 1, 2 DCA, that is the concentration here and it has some concentration here. This 1, 2 DCA, so these are chlorinated hydrocarbon. I have some concentration here. So this is one like type of contaminants. This is called chlorinated hydrocarbon. This is another type of contaminants called like PTEX, like benzene, toluene, xylene, and xylene. So this is PTEX. So here I also plot my concentration, and for this one I just like delineated. So before even I do a transport model, I will do a particle tracking model, and that's like similar to your projects that you will do. So particle tracking is that basically I have some particle here. Remember, what do I want to do? I want to develop like a remediation system, something to capture these plume, like so that they will not go outside this side. So this is my side boundary. So what you see here, yeah, this part here, this is this side boundary here. Yeah, I'm just like zooming at this part here. So this is this part here. This is what you see here. So I want to put like some pumping well, like a pumping well here, a pumping well here, a pumping well here, a pumping well here. So that's my design problem, is identify the location of these pumping well and the flow rate such that the pumping well, like see this particle, this particle, this particle, this particle, this particle will end up in this pumping well. And if this particle ended up like, see, this particle will go maybe here, this particle might go here, this particle might go here, this particle might go here. So if this particle ended up in this pumping well, this means I'm able to capture this plume. So basically, that's so I have two plumes here. I have, or more than two plumes. I have one plume here. This is like this dark one is the light one. Uh, this is like a chlorinated hydrocarbon. This is like a chlorinated hydrocarbon. This is PTEX because you see this is the one here, PTEX. PTEX, and this is some also chlorinated hydrocarbons. That's like this one and this one, like this is a chlorinated hydrocarbon, like you see. This one here would be like this one here. Okay, so that's my conceptual model for the particles that I want to do. In your project, you have to do something like this. In your project like this, you have three design problem. You have to choose one of them. You don't need to do the three of them. You can just do any of them. So in your design project, I'm telling you that there is a pumping well somewhere here, yeah, for municipal water use, and then we also want to put landfill. So what would be the location of the landfill such that if any contamination, in case of any accident, the lining break or whatever, or degraded, any contamination from the landfill will not go to my pumping well. So basically you say, okay, I will put it here, and then you put it by particle tracking. And then you will see would any of these particles end up in this pumping well or not. If any of this particle ended up in the pumping well, means that my this contamination will contaminate the site. And that's similar. Remember this case of this Blackwater movie by John Travolta? You can do this. You can just show. That's exactly how you prove something like this. You say, okay, this is the dump site of these people. I will just put some particle here. I will start pumping from here. This particle will end up here. This means that this site, like this well, is contaminated from this site. That's how you prove these things. And then you take this to court, and that's a very strong evidence. Yeah. Okay. But again, this is just like one representation of, like, remember, a conceptual model is just one representation, a non-unique representation. One could argue that, you just lumped all these guys as one thing. Maybe there is, okay, one something here, but there is maybe also something here and something here. So that's a different conceptualization. And maybe the recharge rate here should be like a little bit higher and something like this. Yeah. So that could be another like representation. Yeah. For the subsurface, one, based on the data we have, one could conceptualize it like this. Another, groundwater hydrology conceptualized like this, or this, and you, like, you can have different conceptualization because you don't have a unique interpretation for your data. We are also uncertain about the layer thickness, so it could be like that small based on some evidence we have, or it could be that large based on also some evidence we have, and we don't know which is which. So if you put all this combination together, so we have like two recharge scenario. So for the recharge, we have like two scenario. For the hydraulic conductivity, for the K, we have like four scenario. For the geology, we have like two scenario. If you take the combination of all this, that would be like 2 times 2, that's 4 times 4, you will end up with 16 model. Yeah. And okay, so now you have 16 model. What do you do with them? Which is the true model? Well, the true model lets the data speak. Like, set up 16 groundwater flow model, calibrate this 16 model, like, means that try your best to make this model like patch what you are observing in the field, and the models that can better represent what we are observing in the field, these are the gold model to keep. Some model will not be able to represent what we are observing in the field. This means that this is a bad proposition, this is a bad idea, we just eliminate this idea. And there are methods for doing this. So there are rigorous methods. This is what I've been doing. This part of my research is how to do this multi-model analysis. Like, if we have like this multiple model, how we can use some rigorous statistical method to be able to eliminate bad idea and keep moving with the good idea. So maybe that will turn out to be like a bad idea, and that's a better idea. Maybe that will turn out like to be a bad idea, and that's a good idea, and that's a good idea. Maybe that will turn out to be a bad idea, and that will be only good idea. So now we eliminate it. So now we have one recharge scenario, we have one geological scenario, and we have two hydraulic conductivity scenarios. So we eliminated this. There's only two models that are remaining. So we started with 16, and then we ended up with 4. But again, that's not important. Like, I mean, if you don't understand much, that's fine. There where I mean, you can check some, you can go to my research website and check some of my publication about this, and then you can learn more about these techniques. But that's not important now. Uh, but the main message is that here is what I want you to learn: that this a conceptual model is a non-unique representation. That's the first thing for my aquifers. The second thing, a conceptual model is something that is I can mathematically describe it. So all these things is basically how the model is formed. So all this could be mathematically described by my groundwater flow equation, because these are the different component of my groundwater flow equation. So now let's get started. So now this was just like a quick overview, and now we will what I want you to do, like, before we get, like, now we will learn about the main steps in modeling, but before we do the main steps in modeling, I want to ask you like this tricky questions that I always ask, and that usually no one get it correct, but we will see. Yeah, if so, this is like the questions that I have for you. So now you are. Uh, this is the questions that I have for you. Uh, now you are like you take this course and you became a groundwater modeling an expert groundwater modeler. And by the way, like a student who took this course before, She is now a modeler in the South Florida Water Management District. Yeah. So you can, I mean, even though it's an introductory course, but you can get this job. Yeah. She was one of the master students. Yeah. And she's now modelers there. An expert groundwater modeler, and your supervisor asked you to prepare a groundwater flow model for Estero. And then what would be your response? So where you respond, sure, I will collect as much data as I can and make a list of additional data needed to build a conceptual model. Would that be your response? Or sure, I will collect as much data as I can and start building the conceptual model. Or sure, I will collect essential data and start building an initial conceptual model, or none of the above. So please pause this video, answer this question, and make sure to upload your, or just click on this link, make sure to upload your screen, your confirmation screen to get credit. So this is like you do this for credit, and then we will look at the answer. But please don't look at the answer. Again, this is not right or wrong answer. Like this is like, don't look at the answer, just answer it first, and then we will look at the answer. That makes it more interesting, yeah? Okay, so stop the video and do this now. Okay, welcome back. So let's look at what the previous student did. So you see, like here we have like two extreme. Like two students said, yes, I will collect as much data as I can and prepare ask for additional data to build a conceptual model. That's one group. And then the other extreme, I will collect essential data and start building the conceptual model. So this is more like on the reserve side. The actual answer is none of the above. Why? Because before you collect any data, before you build any model, you should ask what is the model purpose? Why do you want to build this model? That is the first step in the modeling process. So here, that's the first step in the modeling process, which is the model purpose. What is the model purpose? So so that would be like your first step. Like so, and that's a very important lesson. So uh, I've worked in several like modeling projects before, and the most important thing to define is like what is the modeling purpose, because the modeling purpose will define your data collection. So if that is my modeling purpose, okay, then this and this and this and this would be the data that I would like to collect. And then the modeling purpose will maybe even like if you know the modeling purpose, maybe you will tell them actually you don't even need a model to solve this, to answer this question. Like there are other easy methods, because developing a model, this is a time consuming task. It's time consuming, is also costly task. Like if you want to the USGS to develop like one of this groundwater model for you, they will ask at least for $1 million in 3 years at least to do this, like to develop one of these models. So they are not cheap, they are time consuming. Uh, so maybe like if you can answer these questions without like even using a model, then answer them. Or maybe you can use it with an existing model. So there is already an existing model that is out there that you can use to answer this question. Maybe you just change it a little bit. Maybe you change your boundary, you change your recharge, you change your whatever, and then you can use it. And I have done this before. So like for some management problem, that's what we want to do. Like we want to estimate sustainably like the maximum amount of water that we can extract without having an adverse impact. So I told them, okay, there are existing model. We can get these model and we can change them, like make some change to them, and then this model can answer our question. Because collecting data and setting up this model is very time consuming. This is also true about field data collection. Like I worked with some groups before, and then once they will say, oh, let's go to the field, let's collect this and this and this data. And then why do you want to collect this data? What are you going to do with this data? Is already some data available? If there is already some data that is available, get this data, get these available data, the data that is already there, the data that is already available. Get this data and start building a conceptual model and start building like a model, like a numerical or a computational model, and let this computational model, based on the available data, guide you to where do you want to collect data, where is the most uncertain part of your model, and this most uncertain part of your model, that's exactly where you want to collect data. That is the data that will provide you with the most information. And some some part of your model could be uncertain, but this part of your model is not directly related to your decision. So basically, like, you want to identify what are the part of my model that's directly related to my decision and that are most uncertain. And that is why I want where I will be collecting data. And that's why it's very important before you do anything, whether data collection, whether model development, anything, you define the purpose and you collect all the existing data. You use the existing data, you build a model, and let this model guide your data collection and more efforts that you want to do. And this is called like experimental design, and that's also part of my research. So my research is mainly on my so I'm a groundwater hydrologist, and my research mainly is on uncertainty analysis, and that's what I do. Like, I will see, like, okay, where can we collect data to minimize our uncertainty, or how could we use the existing data to find what are the good modeling idea and what are the bad modeling ideas, like bad conceptualization, bad conceptual models that we can get rid of. Yeah. And I can, if you're interested, let me know in the comments, and I can maybe prepare like a video about this. Yeah. If that's like a topic that is of interest to you, I can prepare like a special topic video about this. Yeah. But anyway, so define your model purpose. So here's your model purpose. So in your modeling report, that's what I would like to see in the introduction. If I didn't see this in the introduction, you will lose points, and then I will know who's not watching these videos. Yeah. Okay. Uh, so I need to see in the introduction, I need to see clear model purpose. So your would be like, we developed a steady state groundwater flow model to study the maximum amount of water. So that is like the design problem number one. Design problem number two and design problem number three might be different. Yeah. The amount of water that can be extracted from new groundwater supply well, given current and future land use and land cover scenario. So that's the model purpose. So what does this mean? This means I need data to build like my conceptual model, like this geological data, hydrogeological data, flow data, so on, boundary condition data, data about the river and river stage, and so on and so forth. But also I need some few like land use and land cover data, current one and future one, because for to taste like this future scenario. So this would be part of the data that I will need. But in your modeling report, that should be clear. The model purpose is like, just you can even make it like a subsection, model purpose. Yeah. So that's very clear, because there is no such thing as one model fit all solution. That's what generally amateur model will do. Like, they saying that, okay, this is one model fit all solutions. This model can do everything. That's because this is not the case. We model for a purpose. Yeah. Okay. So let's move on to the next part. Like, after you do this, you build your conceptual model. So in your conceptual model, for example, you will define your aquifer thickness. This information will be given to you. You did this before, like you put like your hydrogeophysical data, your pumping test data, and you collected all this data. You built your hydraulic conductivity field. You defined your boundary conditions. So you have a river here. You have like a constant head boundary here. You have like a no flow boundary here. Yeah. So we looked at this before. So you did something you did before. You have like a no flow boundary here, and that basically will that would be like your conceptual model. And so I used here. I built this conceptual model with something called like Model Muse. So Model Muse. So Model Muse, this is a graphical user interface for Mudflow model. So Mudflow, these are family of model. Like one is like Mudflow 6 or Mudflow 2005. These simulate flow. But you have like CWAT that will simulate like density dependent flow, like for coastal aquifer, or if you have saltwater intrusion. You have MT3D that will simulate contaminant or solute transport. You have, there are so many of them. So this all called like multi-flow family. So model muse, this is a graphical user interface for this mod flow family, and this is what we will use to set up and calibrate our model. Yeah. It's to calibrate the model, you need another software. It's called BEST, and also Model Muse is a graphical user interface for this BEST. This is the software that you need for model calibration. And this Model Muse made things like several years ago. This was developed by the USGS. Several years ago, groundwater modeling was generally an advanced topic that was taught to advanced student because there was no graphical user interface. There are some graphical user interface, but these graphical user interface are commercial. So basically, some people will get these models. So ground Mudflow, this is developed by the USG as they are free. So they will get these free model. Like these model, you can only run them in patch mode. Patch mode, that means you need to run them using Python, or you need to run them using MATLAB. That's what I did before. I used to run them in this patch mode. Setting up the models, you set up your model with Python, for example, and there is a Python package called like FlowPy for doing this. So you set up your Python, like your model with Python, then you run it with Python, and then you post-process the results with Python, for example, and that make it like these things not accessible. But then some people like GMS, for example, groundwater modeling system, they got like this model like Mudflow, MT3D, whatever. And what they did is that they created a graphical user interface for it. But it's not free. You have to pay money to use it. But and that's why, like, if you don't have license for this, then you cannot teach a course like this. Yeah, because it would be difficult for the student. Like, you have to teach the student first how to use Python and how to do programming to be able to do these tasks. But what UAGS did, they developed like this model Muse, which is a free and very powerful graphical user interface for this Mudflow family. And that's why I am able to teach this in this course, because I don't have license for GMS, but this is free. Mudflow is free, so we can do this. Yeah. So I build a conceptual model, and after you build a conceptual model, you build like you describe this mathematically. So my conceptual model, it will include what? Like, it will include the model domain and the grid spacing. So this is the model domain. The grid spacing here is like 50 meter by 50 meter. That's the grid spacing. The grid spacing along the river, because I want to discretize it smaller, is like 10 meter by 50 meter. So like it is like 10 meter here and 50 meter here in this direction. So in this direction is like 50 meter. Yeah. Hydrologic conductivity field. You did this before. Recharge. So the recharge will be giving to you. Boundary condition. We did this before. Surface water, groundwater interaction. So we have like a river here, and I will give you some information about this river. We will do this now, actually, in this video. Yeah, in the coming slide. Okay, and head measurement. So why do we need head measure? Because what this model will simulate, it will simulate the head. So what this model will do, it will simulate the head here, the head here. At each of these cells, the head will be simulated. Oops. At each of these cells, the head will be simulated. But let's say my model simulated the head here. Now I can measure the head from this observation well. I compare it with what my model is producing. If they match, this means a good model. If they don't match, this means that this is not a good model. And that's what you will do for your project. So in your project, I will give you this head measurement, and you will compare it with what your model is simulating, and you keep improving your model until they match. Yeah. Uh, so here, this is the head observation data. So B1, for example, like this is the X, Y coordinates, this is the head that we measured in the field. And then we will see like what will my model produce. If my model produce like 110 meter, for example, that's very different, yeah? So that means that this is not a well-calibrated model. I need to change my hydraulic conductivity value, and that will make my model calibrated. But then let's say I change my hydraulic conductivity value here, and then now my simulated value, what my model is producing, is 107.9. Now that's a very good match. Yeah, it's only 8 centimeter difference, so that's good. Yeah. So like you are giving like, so that is the data that you will need to build like your conceptual model. Uh, you can also see now, you can also understand something about the flow direction. So here 108, 106. So obviously the flow direction is this direction. So now you understand this. You also get pumping test data, and this pumping test data will help you along with the geophysics data, will help you. This is a plan view. Here, this is the industrial area that you will design. So your design problem, I think, is that you want to do this design area. When you do this design area, that will block recharge. So you'll have less recharge here, which means you will have more drawdown. And in order to mitigate this, I'm telling you, do some nature-based infrastructure, like so infiltration, like you do something that will improve infiltration here, like some nature-based infrastructure features that will improve recharge and mitigate the impact of this, what you're doing here. Yeah, that's like your design problem. Okay, then you have like your geophysics data, and you need to understand this because now I will need to know like recharge data, like what is the recharge in my model here, what how recharge will be reduced when I add this, and what would be the recharge, like how much recharge will I have with this like new nature-based infrastructure. So that's would be all the information that you will need to as part of your conceptual model. Yeah, and then you have your geophysical data, and then you can use your hydraulic conductivity data and your geophysical data, your pumping test data, I mean, and your geophysical data, and then you develop this hydraulic conductivity field. So this hydraulic conductivity field, you did this before. It has like 6 zone. We don't have data here, so that's basically for zone near the river. So like we have a river here, and for zone near the river where no pumping test data was conducting, we assumed like K to be 150. Is it 150? Is it 100? Is it 50? Is it whatever? I don't know, but that's exactly what we will do in the model calibration. Like we will change this from 150 to 100, and we will see, are we getting a better match from what we are observing in the field and what our model is simulating? If we are getting a gooder match, then I will say, okay, maybe let me reduce it even to 90. Oh, my match is improving. Let me reduce it to 80. It's even better, and so on and so forth. So you can do this manually, or there is a software which is called BEST, can do this automatically for you. So basically, it will change like these values, this hydraulic conductivity values. It will change like this hydraulic conductivity values. Like let's say you will define this 8. Like you will say this is K1. Like the minimum maybe could be 5. The maximum could be 15. So it will change like so keep changing like this value from this range that you provide, like here, this you'll say the minimum could be 10, the maximum could be 50. For this one, you say the minimum could be 200, the maximum could be 400, and so on and so forth. So it will keep changing the hydraulic conductivity value within this range until it finds the best, like the hydraulic conductivity value that will provide you with the best match with what you are observing in the field in terms of your hydraulic head, like will provide head. But also, like the head that your model is simulating matches the head that you are observing in the field, like this one. So this is the head that I'm observing in the field. So I'll keep playing with this hydraulic conductivity value until my model simulates something that looks like this. Yeah. Okay. So boundary condition, you also need to define boundary condition. We talked about boundary condition, but let me review what we did before and maybe provide you with more detail. So we have like a specified head value condition. Specified value. Specified value means that I could specify the head. I could specify the temperature. I could specify the concentration. This is called the list boundary condition or type 1 boundary condition. So let me give you an example. So let's say I have a heat plate, and in this heat plate, I will just specify the temperature here. So the temperature here, it could be, I will say like 20 degrees centigrade. That's the temperature here. It could be different. It doesn't need to be the same everywhere. It could be like the temperature here is 20, the temperature here is like 25, and the temperature here is like 2, whatever. Yeah. And this is not just in space, that is also changing in time. So I could specify it not just in space, like at this location, but at this location and at this time. I, I could replace that's called like a specified value. Specified value, why? Because I could specify the temperature So at this space and at this time, this is my temperature. I could specify the head at this space at this time. This is my head, for example. And same with concentration. Yeah. So this is called like a type 1 boundary condition. So let's say if you are looking for groundwater flow, so I specify the specified head. So the specified head at this location, XYZ location, and at this time, this is my head. Like, so my head here would be like 100 meter. So at this X, this Y, and this Z, and this one is 100 meters. It could change in time. So like let's say at this location here, at this time step, this is my head. At next time step, this is my head. At the third time step, this is my head. At fourth time step, this is my head. So it could change. It's also changing in time. So your boundary condition is something that you specified in space and time. And this time could be anything. Could be the next minutes, the next hours, the next days, the next 10 years. Yeah, that depend on your time steps or your the problem you're trying to interest. For the if I want to like specify the solute, for example, for solute transport, I will specify the concentration. Same thing. So that would be like the concentration here is like 10 milligram per liter, 1 milligram per liter, whatever. Yeah. So that would be the specified concentration. The type 2 boundary condition uh, is specified like specified you specify flux condition. So flux condition is not like the head value, but flux condition would be like the flow rate, like how much water is entering at time. Like that would be the flow rate, Q, big Q or small q. That could be like the mass transfer, like how much mass is being transferred, like how much, not milligram per liter, not concentration, but how much like milligram, how much amount of mass is being transferred, or heat, not temperature, but like heat, how much heat is being transported. This is called like type 2 boundary condition. So in type 1 boundary condition, I will specify the head, let's say the head is 100. And then the model will accordingly calculate the flow rate. It will accordingly calculate like how much water will, like giving this head, how much water will enter my model. Or I could specify Q, how much water is entering here. And then my model will calculate the head accordingly. Like, so for this amount of water to enter, I need to maintain that amount of head. Yeah. So that is that's like type 2 boundary condition. Yeah. So here, like I specify the Q, I specify the flux. Type 3 boundary condition, that's a mix. So basically, like let's say I have a head in my river and I have a head in my aquifer. So depending on the head on my river and the head on my aquifer, Q will be determined accordingly based on some constant. Yeah, so there is like, so let's say I have, this is the head on my river is high and this is the head in my aquifer is low. This means that water will flow from my river to the aquifer. This is called like a losing stream. Yeah. But how much water will flow from my river to my aquifer, that will depend on this sea. And this sea is controlled by different factors, like such as the riverbed conductance, like the riverbed, like by what this constant called like the riverbed conductance. And this riverbed conductance is controlled by several factors, like the hydraulic conductivity of the riverbed, for example, and some dimensional factors that I will be showing you later. Yeah. Same for the solute transport, like the concentration gradient will define this one. So here, this is an example of a specified head. Specified head, that could be a river. So a river could be like type 1 or type 3. Type 1, it could be just a specified head. I could just make this like a specified head. And where head here would be 100. And I can assume that this is specified head. Or it could be like a type 3. Yeah. Boundary condition. Or a constant head. Constant head like a swamp. Let's say we have a swamp that has a constant water level throughout the year. Yeah, so the head here would be constant throughout the year. Yeah, something like this. Yeah. Type 2 boundary condition is that you specify the flux. So the flux would be flow rate, like how much water is entering from here or from here or from here. how much water I am injecting or extracting, because that's a flux. I'm injecting something or extracting something. But you know what? It could be also a no flow boundary, like Qx could be equal to 0. That's like a no flow boundary. That could be also like a type 2. Type 3, this is like dependent condition. So depending on the, so let's look here at this example. So let's see. So here is like my aquifer. This is my cell, so I divided it into different cells, and this is my river segment. So I have like one river segment here, one river segment here. So each of this river segment would look something like this. It will have like a length, so that would be the length. It will have a width, so that would be the width, so that would be W, that would be L, and in 3D it will have some thickness, yeah, your riverbed. So like let's look at it here. So you overlap your river over your aquifer. So this is like a bird view. This would be like a cross-sectional view. And let's say the head in my river is here. That's like the head in the river. And let's say the head on my aquifer is like much lower. Like this is the head in the aquifer. Yeah. And if the head here is higher than the head here, or let's say in that case, because I'm showing that water will flow from here to here, so let's say this is the head in my aquifer is somewhere here, just like the head in the aquifer, and this is the head in the river. So if I have high head, so like high energy here and low energy here, this means that water will flow in this direction, yeah, from the river. But how much water will flow? Like how much water will flow from my aquifer to the river? So there is that depend. So like this is the equation for like for Q is equal to Q A. A is like the area, so that's like length time width. And so that's like length time width. And then what's Q? Do you remember Q? We did this before. Negative Ki, and I is equal to negative K delta H over delta. In that case is Z. So Z basically, that would be this distance here. Yeah, that would be the Z. That's the distance where the water will flow. Yeah, your riverbed thickness. And so this delta H over not delta X delta Z. And that what would be delta H? That would be like your head in the aquifer minus the head in the river, because water will uh, be flowing like in this direction. So that's like the head in the river minus the head in the aquifer, or whichever, like you can do it any way you like. You will just, if you did it this way and you get a negative sign, this means that your arrow is wrong. Yeah, but uh, this means that your arrow is wrong. Okay. But so here, that's like the delta H over M. So that would be like your riverbed thickness. And like can I take all these guy? Yeah. K, that's the hydraulic conductivity of this guy. So K, that's the hydraulic conductivity of this guy. Can I take all this guy and call it CR? So CR is like all this guy. And this is called like a riverbed conductance. So that's riverbed conductance. If you have a fault, it's also something similar. It's called fault conductance. So let's solve a problem. Yeah, let's do a problem. So this is from your projects that you will be do. There is a 40-meter river wide in the model domain. The elevation of the riverbed bottom is like 95. The head in the river can be assumed to be constant. So now we have the first piece of information. Head in the river is like 100-meter, yeah, along the area of interest. The thickness of the riverbed sediment is, so the thickness of the riverbed sediment, that's like M. So here, that's like this guy, is, so M is like zero point 0.2 meter. The conductivity of the riverbed sediment, like the K of this guy, like this K river. So K river is 0.02 meter per day. Yeah. The river cell is defined cell by cell in the model. The width and length of the river cell. So the width of the river cell in my model is like 10-meter, and the length is like 50-meter. So I have all the information basically. Calculate the hydraulic conductance. So calculate like this guy here for each cell. Yeah. And by the way, this hydraulic conductance could be different for each cell, because for each cell, your M, like the thickness of the riverbed, could be different. For each cell, the hydraulic conductivity of the river could be different, and the width of the cell is also could be different. Yeah, but that's easy. So we have this guy, we have this guy, we have this guy, we have this guy. Then we can solve for this guy. So pause the video, try to solve it, and make sure that you get the same answer. And that would be part of your report, and that would be something you need to include in your modeling report as well, like this calculation and how you reach this calculation. Yeah. So that would be like the answer if you got it correct. Okay. Now here is another problem. Now here I want you to calculate Q, like how much water will move from like the river to the aquifer or from the aquifer to the river. So find the exchange flow rate between the river that interact and groundwater system through head-dependent flow boundary condition modeling using this one. So now I'm giving you the river stage is 12, the aquifer, so the aquifer at this IJK at this location is 10. What does this mean? So I have higher head in the river than in the aquifers. This means that water will move from the river to the aquifer. This means that this is a losing stream, not a gaining stream. Means it will get recharged from the aquifer. Losing stream means that water will flow from the river to recharge my aquifer. Okay. So like this information is giving, so you can substitute this here, but you need to calculate this guy. So to calculate this guy, you need the hydraulic conductivity of the riverbed, you need the length of each river reach, you need the width of each river reach, and you need the thickness of the riverbed sediment. So if you did this, then you will get something like this would be your CRs, and you substitute here, that would be your Q, and uh, uh, that would be your Q, and then obviously head in the river is higher than in the aquifer, so flow would be from the river to the aquifer. Yeah. Okay, now fine. So now we have our conceptual model. We know our boundary condition. We know recharge. Recharge will be giving. I mean, I don't show it here, but it will be giving in your mod, like in your assignment, the recharge value. Uh, so what? Okay, what do we do next? So next, like once we have a conceptual model, we need to see like represents this mathematically. This is the mathematical equation that represents this conceptual model, and we know that. So here, this is my k. This is the h value that the model would be solving for. This is w, the recharge. This is sustainable yield. For our case, it's a steady state, so that guy would be all zero because it's a steady state. We don't need this one, but we need like recharge. Yeah, this is the w, the recharge. Yeah? But recharge we're getting here. So we need to find someone that can solve this for us. We know that this has no analytical solution, so it need to be solved. This mathematical model need to be solved, and of course, this mathematical model. One thing is missing here. I didn't put it here, but I expect you to do this in your is the boundary condition and initial conditions. That's part of your mathematical model. So your mathematical model should also involve the boundary condition and initial condition. So in your modeling report, I want you to include this. This is our mathematical model, and this is the boundary condition and initial condition. Mudflow does not solve this equation. Mudflow, because this equation is very difficult to solve numerically, even numerically. So Mudflow solves the equation for the unconfined aquifer and then correct for H. Yeah, but your modeling report, you can either write this equation and clarify this, or you can just go to Mudflow manual and copy the equations that Mudflow is solving. You just copy it from there. That's even better. And this is, we'll say, but you can select your modeling code. So Mudflow, what Mudflow will do, it will solve this equation for you numerically. Yeah, so it will, like, you have your model, you create your input file, it will take your input file, create the numerical model, and solve this equation and find h here, h here, h here, h here, h here, h here. In each of these cells you will be calculating your hydraulic conductivity value. That's what Mudflow will do. But Mudflow is not the only code out there. So that's your mathematical model, and then your modeling code. So Mudflow is just one modeling code. Mudflow is called finite difference. So that's like where you divide your model domain into cells like this. This is called finite difference. And then you, for each cell, you find the hydraulic conductivity field. There is also other models that are like finite elements. So finite elements, it will divide your model domain into elements, and then for each element, it will find the head. Yeah. And there's also MudFlow, the new like non-structured grid. Yeah, that's something also different. MudFlow 6, the non-structured grid. But anyway, these details are beyond like the scope of this course, but like example of finite element codes would be FeeFlow. That is but it's not free and it's very expensive. Example would be like Sutra. Sutra, that's a finite element density dependent model developed by Cliff Voss for groundwater density dependent groundwater flow. So that's very rigorous model to use. Finite element. I used it before in Hawaii, and I worked also closely with model developer like Cliff Voss for Cliff Voss. He used to work in the USGS. He's now retired, but so that's also another finite element model. Okay. Uh, and then what else do you do? Yeah, so here, this is like an example of this is just like for this finite difference model, you can have two solutions like mesh centered or block centered. Mesh centered, you'll estimate like the head here, here, here. Block centered, you'll just estimate the head here. Yeah, so that's the difference. So let's say, for example, this is my boundary. Like let's say this is my boundary here and my boundary here. And I know the head here is like 110 and the head here is 100. What would be the head here? Maybe 109.5. What would be the head here? Whatever, like 108.5. What would be the head here? 100.5. Yeah. So I could estimate the head either here or here. Usually we use like not the mesh centered, like we generally would use like a block centered. So for the mesh center, you have like, so your model output, like if you are using like a mesh centered, uh, uh, if you are using like a mesh centered thing, your model will be like 5 by 10 or whatever. Okay. So you set up your model, and now this is what we will be doing next. So this mod flow, we talked about this. We talked about model muse. Uh, then we do the model calibration. Calibration, you set the calibration target like head, you estimate your parameter, you change your K, for example, and then you see like, is my head that I'm observing similar to the heads that I'm measuring or not? And then you process the results accordingly. So this is the model that we use for calibration. This is how we will you see how you will install your model flow and mod flow model, like the tools that we will use. And this is the model setup and calibration tutorial. So that's what you will be learning next. And that's it. And I will see you like in the